Okay, so our next speaker is Todd Christopher. Todd is currently a PhD student in the Department of Mechanical and Aerospace Engineering at the University of California, San Diego. He is working with Professor Stefan Llewellyn Smith. Today, Todd will be talking about hollow vortex in a corner. Todd?
Great, thank you. Thank you for having me. Thank you for everyone else for the great talk so far. Vikas has pretty much covered the first slide. So I'm Todd Christopher. I'm going to be talking to you about a hollow vortex in a corner. So let's get right to it. Here's the question. Here's the problem we're trying to solve. What is the shape of a hollow vortex at rest in a corner? So now it's just a multiple choice question. You see the options here. One of these is correct. I won't tell you which one until the end. You can pick your favorite now. I particularly like the star shape in the bottom right, so I'll be pulling for that one, but you're welcome to select any one you want. And this is the question we're going to try and answer by the end. So you'll see at the bottom, I've selected one of those as a temporary possible correct solution, but don't worry, it could still be any of them. It could still be the star shape by the end. But how do we find the shape? So physically, what we're going to need to do is we have this corner and we have some sort of vortex there. So we're going to be balancing circulation around the vortex with some sort of flow from infinity. Of course, the boundary is going to need to be a streamline, the corner boundary and the vortex boundary. And we're going to try and hope to recapture and recover the point vortex solution as we get really far away from our hollow vortex. So mathematically, what we're going to do is we're going to work with the complex potential. We're going to map the problem to a simpler domain. So the canonical domain here is going to be the annulus. We're going to meet conditions with some sort of magical new function that we just heard about in the last talk. And the solution is going to be z as a function of zeta. So it's just going to be the map from the annulus, the simpler domain, to the physical domain z. And you can see that these are the two maps here where we have the corner domain on the left and then the annulus on the right, with the blue corresponding to the hollow vortex, the black corresponding to the corner itself, and then the red we'll see is going to be an image hollow vortex. So the governing equations, we're going to be working with 2D, inviscid, and compressible and rotational flow. All that means that we're going to just use the complex potential, and we're going to be able to write down complex potentials for various things. So if you've forgotten what those look like, here are some examples. Very simple. You have uniform flow. You can write down a point source and a point vortex. And we're going to write some of these down and try and meet our conditions using that. So how do we construct the map? Well, in order to do it, it turns out that if we're able to write down the complex potential in the annulus, W, so that'll be W throughout, and then if we're also able to write down the complex velocity expressed as a function of the annulus variable, then we can relate the two through the chain rule, rearrange, and then we'll have dz d zeta, and we simply integrate that, and then we have our map. So we have z as a function of zeta, and that tells us that all we really need to worry about is constructing the complex potential and the complex velocity as a function of the variable in the annulus. So that's what we're going to spend the remainder of the talk doing, is trying to construct the complex potential and complex velocity. So let's start really simple to warm up for the procedure that we're going to be using. And instead of a hollow vortex or even a point vortex in a corner, let's talk about the absence of a point vortex in a corner. So it's very simple, but we'll follow the same procedure. Basically, map to a simpler domain. We're going to force the boundaries to be streamlines. And then if we have any other conditions, we'll enforce them. So in this case, very simple. We just unfold the corner to a half plane. So then in the half plane, we write down uniform flow. That makes the boundary a streamline. And then we map back, we have our complex potential. So very simple here. There aren't really any other conditions except for just having it be a boundary and having the uniform flow be the right speed, but we'll follow the same procedure. So let's move now from the absence to the presence of a point vortex in a corner, where things get more interesting. So simpler domain here, we're still going into the half plane, but in order to force the boundaries to be streamlines, we use the method of images, and we do have another condition to enforce. We need a stationary point vortex. So we go through, it's a little bit more complicated, use some algebra, get a correction term, but you do it, and at the end of the day, you find you can write down the complex potential in the half plane, and that tells you then what it is in the corner. So this is going to be particularly important because, as I mentioned, we are going to try and get the same behavior for our hollow vortex far away from the hollow vortex that we have here for the point vortex. So I'll talk about a few properties of the point vortex solution. There's streamlines there, same complex potential as the previous slide. And what we want to note is that we have one stagnation point along each side of the corner. So you can see that from the streamlines. So you have here, you see it's hitting the side, and we have stagnation point there. And then the other thing to note is that as we go far away, let's say up here towards infinity or down here towards 0, even with the hollow vortex, we think it's probably going to look pretty similar to the point vortex. So that's the condition that we're going to enforce. So before we can do that to the hollow vortex, we have to know what hollow vortex is. And it's kind of just this region, closed region of steady state, constant pressure. The boundary is a streamline, and we have some sort of circulation, specified circulation around the boundary. And then along the boundary, given that we have constant pressure, and then given that we have Bernoulli's equation, we can conclude that the speed is also constant. So that's a condition we're going to use. We're going to need the speed to be constant along the boundary, and we're going to need the boundary itself to be a streamline. Okay, so hollow vortices. So someone else solved a very similar problem with hollow vortices over a century ago. So let's have a brief historical interlude then. That was H.C. Pocklington. And I've selected a few interesting quotations from the Fellows of the Royal Society biographical memoirs of him. So Henry Cabourn Pocklington was an unusual man. He rarely spoke, not even to his own brothers and sisters. And he refused to take up residence in St. John's College, Cambridge, pictured above, when he was elected to a fellowship because he dreaded the social contacts at the high table. So sounds like a pretty relatable guy. And why is he relevant? So he worked on a problem that was translating hollow vortices, 1894 here. And you see, it's the same thing that we have. If we unfold the corner so that it's no longer a corner, simply a wall, then translating vortices is the same thing as stationary vortices with some sort of uniform flow, switching the reference frame there. So we're going to take that and instead start to consider different angles. So in order to solve the problem, we're going to use conformal mapping, just like we talked about with the simpler case, point vortex in the absence of a point vortex. So the procedure, again, we map to a simpler domain, force the boundaries to be streamlines, find out what our other conditions are, and enforce them. So the three maps here, you see we're going from the corner into a half plane. We are then introducing an image hollow vortex and then mapping into the annulus. So the corner and the vortex boundaries end up going to circles in the annulus and zeta. And we can assume, we can imagine this being stretched or shrunk. We can assume the outer radius is 1 and that we just don't know what the inner radius is. We can call it rho. The middle circle radius, which corresponds to the corner boundary itself, isn't yet determined, but we'll see that it's square root rho. So just as a reminder, what we're trying to do is we're trying to construct W and dWdz, the complex potential and the complex velocity in the annulus. And once we do that, we'll have our map V as a function of theta. So in order to start constructing the maps, now that we have what we want them to look like, we want to be able to write down W and dWdz. So we're going to think of our conditions geometrically as conformal maps themselves. So one of the conditions you recall is the boundaries need to be streamlines. So that means mathematically that we need the imaginary part of the complex potential to be constant. So we can think of that as meaning that the imaginary part, it needs to take this map, whatever the map is for the complex potential, it needs to take things to a horizontal line, right? So we need it to be a parallel slip map. So both boundaries need to go to parallel lines, but even further, they need to actually go to horizontal lines. So we need some sort of map that takes things from the annulus that are circles into lines that are parallel and in fact horizontal. Okay, so that's the geometry of the complex potential. For the complex velocity, we need constant speed on the boundary. That came from constant pressure inside. Bernoulli's equation means we have constant speed. And mathematically, that means that the absolute value, the magnitude of dWdz needs to be constant as I go along the circular boundary in the annulus. So we can think of that then as being a map that takes circles to circular arcs, which we can call a circular slip map. So as I go along the boundary in zeta, then I need dWdz to not have its magnitude be changing. Okay, so we've thought of these geometrically. If we can write down these types of maps, then we can start to write down what W and dWdz look like. So let's go for it. So the construction of the complex potential, let's just assume that we have these maps and they have the properties that we hope they have. So for the complex potential, we need a parallel slit map. It's going to take circles in the annulus to parallel slits. So that means for magnitude of zeta being constant along rho and 1, the argument of our parallel slit map can't change. So they're lines. The argument can't change, and just whatever it is. In order to make that horizontal, we can simply multiply by an exponential with the appropriate phase, and that'll make it horizontal. So there already we have a little bit of room to play with. Another thing we can do is we can add I log zeta. The reason is that it's not going to do any harm on the boundary. So if we add them together, we see that the I log zeta is going to have, as zeta is going to be a constant magnitude, then our imaginary part is not going to change. So we have this most general form, then we have the phase factor fixing the parallel slit map to be horizontal, and then we can add I log zeta with anything in front of it that we want, and we'll meet that condition. So that's how we do the complex potential. Similar arguments for the complex velocity. So let's just assume we have the circular slit map so that as we go along the circles in the annulus, then the complex velocity is also going to be along a circular arc so that the magnitude of the circular slit map is going to be constant. And we see that we can raise that to any power we want. It's not going to change the fact that it's constant along a circular slit. And another thing we can do is we could multiply by any power of zeta, because again, zeta, the magnitude of that is constant. So it doesn't matter, multiply by that, any power we want, we still are left with a map that takes circles to circular arcs. So then the most general form based on this reasoning that we can think of is to write dWdz, complex velocity, like this, as this sort of possibly really long product of circular slit maps that are raised to some sort of power. And then we have this arbitrary power of zeta in front. So it's very general, but it gives us a lot of room. We can pick exactly what we want to have for zeros and poles, because it'll turn out that these functions are going to have simple zeros at this third argument there. And we can control the behavior that way. And we can choose the exponent to get the right behavior for the power that we want in the far field to match up with the point vortex solution. So assuming then that we have these maps, we can write down these general solutions and hope to make some good progress. The question then is, do these maps actually exist? So yes, they do. And just like Peter talked about, they're constructed using the Schottky Klein prime function. I'm not going to go into detail either. Basically, it's just a generalization of beta minus A to multiply connected domains. And as Peter mentioned, it depends on the domain details. So in this case, it depends on the relative size of our circles in the annulus. And as you go to higher connectivity, then more parameters get involved. For details, you can see Darren Crowdy's book that just came out recently on solving problems in multiply connected domains. So the problem that we're doing now is similar to the Pocklington problem, as I mentioned, and that was re-expressed and resolved with the prime function by Crowdy, Llewellyn Smith, and Freilich in 2013. Previously, it was done with elliptic functions. Okay, so these maps do exist, and that means that we can construct complex potential and the complex velocity. How did we do it? We thought of the conditions as slit maps, guessed the most general form for each case. We have a lot of constants floating around now. So how do we determine what they are? Well, basically, we're going to match the circulation. So there's a given circulation. We match that. That's not too bad. We can use this A2 up here with the log. We match the point vortex behavior at 0 and infinity. So that's how we're going to determine what the powers are here and where we have what some of these other parameters are for the circular slit maps. And then we match the point vortex behavior at stagnation points. So that's especially going to be these simple zeros here. We're going to want that to match up with where the stagnation points are. So that's where the velocity is going to be 0. But in order to do that, we have to know where these points go. So 0 and infinity in the physical plane and the stagnation points in the physical corner, where do they go in the annulus? To know where they go, we use symmetry. And so we see that once we get into the half plane, we're starting to have and assume a lot of symmetry. So we've used an image vortex, which has this nice symmetry that's simply reflected about the vertical axis. We also are assuming symmetry about the horizontal axis here. And we're going to assume that when we go into the annulus, those symmetries carry over. So here, reflection about a line in the half plane, now since we're in the annulus, is going to become reflection about a circle. So reflection about this vertical line now becomes reflection about this circle between the blue and the red, the black circle. And that's how we determine what the radius of the circle is. These are kind of inverse circles of each other, and that tells us the radius of the black circle must be square root rho. Also, we can get that the point 0 and infinity. So here it has to be, we're assuming symmetry about the horizontal axis. So the same symmetry should hold here, which is we can assume it's again along the horizontal. So 0 and infinity in the annulus are going to be also here along the horizontal axis. And they still have to be along the black corner boundary. And then finally, the stagnation points. So here they're circles. They're going to go to somewhere along the black circle in the annulus. And we, by symmetry, know that one must be the complex conjugate of the other. All that to say, we basically just use symmetry to determine where these points go. So we've assumed a lot of symmetry in the problem in order to write down where these points should be. So we do that, we figure out where the points go, we match with the point vortex solution, all the conditions, and this is what we end up with. So basically what we had before, this complex potential doesn't look so different. You have a parallel slip map, you see we've got an angle pi over 2, and then the phase factor to make it horizontal, and we're matching the circulation here. And this is actually the same potential that comes from the Pocklington problem, so nothing's changed there. But you can see that the complex velocity is going to be different because it has this exponent that has 1 minus the corner angle over pi. So if I unwrap the corner all the way to pi, this entire term goes away, and we're left with the Pocklington problem of translating vortices, and it is in fact the same. But we don't have that here, so we have these extra terms, and these are going to be matching behaviors of the point vortex with the arbitrary angle corner. So that's going to have, you see this power in here, and we basically are just recovering the point vortex solution as we go close to the corner, far away. Over here, that means close to 0, close to infinity. We expect and match and enforce that it looks like the point vortex solution to get these constants. And you see that the arbitrary power of zeta ended up being -1, and that came from matching the speeds must be the same constant on each boundary. So we do all that, we enforce all the conditions, but we're still in fact left with a couple unknowns. One of those is rho. Now this doesn't pose much of a problem because we can simply vary rho and get different solutions. And we'll see that that's going to essentially just control the size, the relative size of our vortex, how much space it's taking up in this area here. So really small rho, you can have really small hollow vortices. Large rho, you're going to get much larger hollow vortices. So that's fine, but we do need to know where the stagnation points are. And that is going to come from enforcing that the map be single valued. And the way we do that is we have to do an integral. So we have to guess, essentially sweep through a lot of different values. We know that the stagnation points are on this circle, but we don't know where they are. So we guess what the angle is going to be, do an integral, see if it's single valued. If it is, we keep trying other angles, and then eventually we hit on the right angle, and we have completed these the complex velocity, complex potential. And then we can, as we saw earlier, once we have those, we can construct the map. So then we simply take the derivative of the complex potential here and use the chain rule and integrate like before and construct the map. So then the moment you've all been waiting for, once we do that, what does it actually look like? So remember, this was just a temporary thing that we assumed the shape could be, but it could have been a star shape, could have been a square, could have been a triangle, some sort of ellipse, could have been anything. So hopefully you remember what you selected for the multiple choice question at the beginning. For the big reveal, it is in fact D here. So it is in fact this, though maybe not one of the more exciting ones, but this is what it looks like. And this is for a specific angle of pi/3 and a specific rho value of 0.3. And I'll show you on the next slide how you can change rho and the angle, and you get all sorts of different shapes. So this is what that looks like. These are not streamlines, so all the previous lines are streamlines. These are actually just solutions, so they're shapes of hollow vortices that on their own solve this problem, right? So I've just overlaid them for a given corner angle. I've overlaid solutions corresponding to different values of rho. And as rho becomes larger, this starts to fill in this space. And they're all scaled, normalized, so that the stagnation points here and here are unit distance from the origin. You could also scale it by the centroid, and then the stagnation points would be different, and so you get slightly different looking pictures, but the shape would be the exact same. And you see that they all, when they get really small, they shrink to kind of this point, and that is in fact the exact place where the point vortex is for the same conditions. So that tells us that we've gotten it right, certainly in the small limit when it reduces to the point vortex solution. And interestingly, so you open it up, you open the corner up here, you recover the Pocklington translating vortices case. And then as you open it even more, you don't really have a corner, some sort of inverse corner, and you get kind of a bean shape, which is very fun. And if you open it enough, then you actually can get solutions that cross here. So you get unphysical solutions that still they connect with the shape, but they go into the corner, so they don't work physically. Okay, so in summary then, what did we do? We found the shape of a hollow vortex at rest in a corner. How did we do it? We viewed the conditions as conformal maps. So we thought geometrically, and that allowed us to start figuring out how to actually write down the complex potential and the complex velocity. We decided we need maps with certain properties. Lo and behold, we were able to use this Schottky Klein prime function to construct those maps. Once we had the maps, we were able to use the chain rule to find dz d zeta. The map we were looking for was the integral of this. So what I did was numerically integrate to get this map, and all the details are in a paper from earlier this year. So future work, I mentioned that we did this integral numerically. A nice thing to do would be to find some sort of analytical or closed form of the solution, because it does get difficult numerically at certain points. It would be nice to have a closed form solution, and it's possible that it could be written down. Other things would include looking at the stability of these solutions. We started to do that a little. It then gets fairly complicated and depends on kind of what kind of perturbations you look at for stability. But we suspect that most of these solutions are not stable, especially as you open the corner beyond the angle of pi. The other thing is we assumed a lot of symmetry. So you could try and find asymmetric solutions, or maybe even solutions just with different symmetry. Maybe the star shape is still out there waiting to solve this equation if you assume some form of different symmetry. I'm not sure. I wouldn't quite know how to start going about that, but it would be a very nice thing to find. And then finally, you could generalize this to higher connectivity for special angles. So that's the one bit that I'm actually going to talk about. I'm going to have one slide on that because it's fun to look at. So for certain angles, you could, instead of considering unwrapping the corner and then looking at the half plane, you could just use the method of images immediately. One of those would be the angle of pi/2. Any other angle would be just as long as they fit evenly into pi. So here it's pi/2, and we can imagine here's our physical vortex. We put image vortices over here to satisfy the condition that it's the streamline. And all that symmetry I talked about is the same idea, but it becomes a little bit more complicated. We're considering symmetry about all of these lines, essentially. I'd like this boundary to go to this boundary when it's reflected about the blue line y = -x. Same story for y = x. I also want to insist on symmetry basically about every reflection of a line. So then I can go into not the annulus anymore, but still inside the unit circle. And I can have this map where they all go to circles. And again, reflection about a line often becomes the fact that they have to be reflection to each other about a circle. They're kind of inverse circles. And so you see here, for instance, this smallest circle, if I reflected about this dash of blue line, is going to go to the large circle, which corresponds to this going to this. So that's the gamma 0 is C0 here, gamma 2 is C2. So they go to each other. I'm reflecting about that. And then also, if I reflect about any of these circles, or any of the boundaries in the y equals x negative x, these need to go to each other. So it's a fun construction. Connectivity is higher now, right? Now we have a quadruply connected domain. And so then you have to start using the prime function package instead of a simple product representation that you can use. And I started doing this, and somewhere along the way got very far, but maybe because of these issues with computing it close to certain points on the boundary, wasn't quite able to finish getting an answer. But it would be made even more interesting to get an answer here if you could write down a closed form solution in the other domain, doubly connected, and then you could start connecting prime function identities between different domains. So that remains to be seen if it can truly be done, but it's one thing that would be interesting to see. Finally, I'll show a few of the references that I mentioned during the talk, the recent paper here, some of Darren's work, and then the old Pocklington paper. And that is the end. Thank you for listening.
Thank you very much, Todd, for a wonderful talk.